Also in 2022, we released the physical media attachment sublayer for CAN SIC XL. This is for the transceiver chips for CAN XL networks. We will come to this in more detail. This year, we have released in ISO, the ISO DIS 1189-2 document. This includes the CAN high-speed physical media attachment, including SIC and SIC XL functions. So this is just released and will be then at the end of this year, I hope, released as an international standard. In the moment, it's just a draft. Okay, let's go in some more details. The CAN high-speed transceivers, as I said, since 1992, they was available. And I remember quite well that in those days, Philips Semiconductors provided the first engineering samples, and they support 1 megabit per second, as most of the competing products on the market today. There are not that many products available which can't reach 1 megabit per second. But historically, there was also versions available just supporting 500 kilobit per second. Nowadays, many of them are limited at the lower end to 40 kilobit per second because of electromagnetic compatibility requirements of the automotive industry. In the beginning, those chips were capable also to run at lower bit rates up to 20 kilobit per second and even lower. In 2016, we introduced the improved CAN high-speed transceivers, providing an improved symmetry. This is needed for CAN FD communication, and this is why we have released them. ISO 11898-2 from 2016 specifies 2 parameter sets, and one is stricter than the other regarding the symmetry. Unfortunately, in the standard, the tables providing these parameters are called 2 megabit per second parameters and 5 megabit per second parameters. And people think that they can achieve these bit rates by just using these transceiver chips. But this is not true. The achievable maximum bit rate is not determined only by the chosen transceiver. You also have to consider the topology, the selected physical layer components such as cables, connectors, galvanic isolations, additional circuitry, and the location of termination resistors. So don't be confused if you do not reach these values, even if you use those transceivers. The physical layer is more than just the selection of a transceiver chip. The CAN high-speed transceivers for those you use normally the non-return to zero coding. The nominal differential voltage for dominant bit is 2 volts. The CAN high line is driven to 3.5 volt and the CAN low line to 1.5 volt. And we have also the recessive differential voltage with 0 volt nominal, and then CAN high is driven to 2.5 volt and CAN low is also driven to 2.5 volt. As I said, the arbitration bit rate is normally in maximum 1 megabit and in minimum 40 kilobit per second. There are 2 parameter sets described, one for PMA implementations limited to single bitrate solutions, meaning for classical CAN, and another parameter set for flexible data rate implementations for up to 5 megabit per second. In the past, there was, as I said, also something for 2 megabit, but I think that most of the new implementations will just support the stricter symmetry parameters. The achievable bitrate depends, of course, still on the topology and some other physical media dependent sublayer components, cables, connectors, etc. Those CAN high-speed transceivers can support optionally a low power mode and partial network functionality or selective wake-up capability. New and not so new, so to say, are the CAN SIC transceiver. These transceivers provide a signal improvement capability. This means they are able to suppress ringing on the network lines by means of a dynamic impedance reduction. There are two approaches specified to suppress the ringing when receiving or when transmitting. The second approach, meaning the transmitting, is currently the dominating one and implemented in several CAN SIC transceivers. With CAN SIC transceivers, you can operate the CAN FD or CAN XL network with up to 8 megabit per second, depending, of course, on the physical network design. But this is also true for challenging topologies. You can achieve this. The minimum bitrate is 40 kilobit per second. And those transceivers are often pin compatible with the classical CAN high-speed transceivers. The CAN SIC transceivers are specified in CIA 601-4, and this document has been submitted for the next edition of ISO 11898-2, which has just passed successfully the draft international standard ballot, but we have still some comments pending and we have to observe them and to resolve them. For those SIC transceivers, we also use a non-return to zero coding. The dominant and the recessive bit level is the same as with the high-speed transceivers. However, the arbitration bitrate is limited. The maximum is, let's say, 500 kilobit per second. We come to that in more detail. It could be also a little bit more, depending on your network design. Here we have the parameter set Z for flexible data rate implementations, a maximum around 8 megabit per second, depending, of course, on the other physical layer design elements. You can also achieve 1 megabit in the arbitration bitrate, but then you have to limit the assignments to CAN IDs. I will come to this in a bit. What is the reason why we can't reach 1 megabit per second? You may know that we need to have the propagation delays for the SIC transceivers, and this is limited, of course, because a small time we need to suppress the ringing, and then the remaining time where the sample point could be located is smaller. All nodes need to read dominant state of the winning node for the arbitration process. This means all SIC nodes driving active recessive need to have finished their SIC time before the sample point is reached for all nodes, depending on the network. This limits either the arbitration bitrate or the maximal node distance propagation delay between the nodes. You see here on this figure that we have here the net bitrate, which we can, that we have the longest propagation delay given here in here, and we have the arbitration bitrate which we can achieve. And if we select, for example, a sample point at 80%, then we are limited at this point to about 667 kilobit per second. Otherwise, we will not detect properly the dominant level at the sample point. And we can overcome this when we would choose a smart assignment of CAN identifiers. Let's come to the CAN SIC XL transceivers. They also provide SIC capability. This means signal improvement capability, so that we have also the reduction of the impedance in a small time to suppress ringing. Those transceivers operate in two modes. They support non-return to zero, as you know it. This is called the SIC mode, and the PWM, pulse width modulation coding. This is called the fast mode. When using the fast mode, the error signaling needs to be switched off in the CAN XL protocol controller. This means there is no data consistency provided anymore on the data link layer, and error handling needs to be implemented in other OC layers, for example, the transport layer. And as said, for the CAN SIC transceiver, also for CAN SIC XL transceivers, the bitrate is limited to 667 kilobit per second. The CAN SIC XL physical medium attachment was originally specified in CIA 610-3, has been submitted for the next edition of ISO 11898-2, which has passed just successfully the ballot, and we will implement the submitted comments, and then this document will be released. There was no negative vote. In the fast mode, normally the bit coding and voltage levels in arbitration phase are the same as in the CAN SIC transceiver. However, in fast mode, there is some differences. We do not transmit anymore with a voltage, with a differential voltage of 2 volts. We just have 1 volt, positive and negative. Level 0 representing a logical 0. There we have plus 1 volt, meaning on CAN high we have 3 volt, and then CAN low we have 2 volts. The level 1, which represents the logical 1, has a differential voltage of minus 1 volt. CAN high is 2 volts and CAN low is 3 volts. The achievable data bitrate is 20 megabit per second. However, this can be only achieved if you have short cables and you have a proper proper designed topology, and all the PMD sublayer components are according to this high speed properly selected. So a first summary, the CAN physical layer scalability. So in classical CAN, features a high-speed transmission with non-return to zero coding, with bit rates from 40 kilobit per 1 megabit, depending on the network length. Of course, we have still the dependency on the length. So at 1 megabit per second, we can reach up to 25 meters. And if you lower the bit rate, you can, of course, go for longer distances in the network. CAN FD features also a high-speed transmission with NRZ coding. The arbitration bitrate is the same as in classical CAN, and the data phase bitrate is up to 2 megabit plus, using not optimized network topologies, and up to 5 megabit using networks with 2 nodes. If you are using in CAN FD the SIC transceivers, you can go up to 8 megabit per second, even when using not optimized network topologies. How far you can go depends highly on the selected topology and the components which you have selected. In CAN XL, we can use the optional SIC XL dual mode transmission with PWM coding. We can go up to 10 megabit per second using hybrid topologies. But in this case, is also the arbitration bitrate limited at 667 kilobit per second. If you're using CAN XL networks, you can run all formats when you're using NRZ coding. In this case, you need to configure 3 bit rates: the arbitration bitrate, the CAN-FD data phase bitrate, and the CAN XL data phase bitrate. And the CAN-FD phase bitrate and the CAN XL data phase bitrate could be different. So all the transceivers on the market can operate NRZ-coded bit streams. No doubt on that. The arbitration bitrate, as I said, is limited to 40 kilobits to 1 megabit. And if you're using the SIC transceivers, then you should use maybe even only 500 kilobit or 667 kilobit per second. The data phase bitrate, new transceivers feature improved symmetry parameters and SIC functionality, and we highly recommend to use SIC functionality for CAN-FD networks. The CAN SIC XL transceivers support PWM coding in the data phase. The mode switching is caused in 2 steps. So we don't go directly from the 2 volt different voltage to 1 volt or 1 volt differential voltage. We do this in 2 steps in order to avoid EMC issues. The bit rate ratios which you can achieve, data phase to nominal, is 16:1 in CAN-FD and 40:1 in CAN XL. And the mode switching is done by means or is controlled by the CAN XL protocol controller, and this can be done in each CAN XL data frame. And therefore you have the ADS and the DIS fields in the frame, which gives you then control on the coding. CIA provides plugfests for those companies implementing the transceiver chips so that they can prove interoperability of their implementations. And we have done for CAN XL in May last year, the first one. We tested different prototypes of those implementations by Infineon and NXP. And we used bus topology with short stubs and wiring harnesses provided by Mercedes and Volkswagen. In April this year, we will continue to prove the interoperability of implementations. And we expect that Bosch, Infineon, NXP, and Texas Instruments provide some transceiver prototypes of transceiver chips supporting the fast mode. And we will use bus topology with short stubs, as well as a double star topology, which we have pre-tested in January 2023, so a couple of weeks ago. These are some results from simulations. You see here that there was a 10 megabit per second star topology tested with symmetric stripes of 4 meter by 5 meters. You see that there was 2 nodes terminated and that the waveforms looked quite well. And there was no problem detected in the simulation. Also in practice, this network has been tested. And so we have the terminated receiver and we have an unterminated transmitter, but it looks quite well. Also 10 megabit was achieved with a 3-star topology, with nearly perfect symmetric waveforms. You see that we communicated between node 8 and node 3. Both were unterminated, and the others, node 2 was terminated and node 1. And we have really a strange topology with 3 star points and a lot of unterminated stubs. with different length. And this, I think, is some of a worst case simulation. And also in practice, this was proved. And you see that the results are quite good. And we will do more in the next Plugfest in Detroit. So how this fits all together with the three CAN generations. We have the classical CAN introduced in 1993 as a standard, and before it was introduced in 1986 as a prototype. Then we have CAN FD and we have CAN XL, which was a couple of years ago started to develop. And last year we have released the first document specifying the CAN XL protocol. So what are the features of these three different generations? You see that the data field length is increased from 0 to 8 byte in the first approach, the classical CAN. CAN FD enlarged this from 0 byte to 64 byte per frame. And in CAN XL, we have a length of 1 byte to 2048 bytes in the data field. There was a priority identifier. And in classical CAN and CAN FD, there was specified an 11-bit identifier or base frame format and a 29-bit identifier. This was the extended frame format for both classical CAN and CAN FD, and the only difference was the length of the data field. In CAN XL, we have just an 11-bit identifier field, the so-called priority ID field, and this contains just the priority. In classical CAN and CAN FD, the identifier was also used for address purpose, content-wise or node-wise. And the addressing is, so to say, implemented in the identifier in classical CAN and CAN FD. Therefore, we have there an 11-bit or 29-bit possibility. And in CAN XL, we have a separated field, a 32-bit acceptance field, where we put the address content, indicating the content or a node address. We have also then some additional new functions like the service data unit and the virtual CAN network ID, which was not available in classical CAN and CAN FD, but this is not physical layer related. This is for the higher layers. Bit stuffing was dynamic in classical CAN, and in CAN FD we have a dynamic and a fixed stuffing in the CRC field. In CAN XL, we have a dynamic in arbitration field, the bit stuffing, and in the data phase we have a fixed bit stuffing. This has some advantages, this is a matter of the data link layer at the end. The CRC polynomials was also different. In classical CAN, we have a 15-bit polynomial. In CAN FD, we have a 17-bit or a 21-bit polynomial, depending on the length of the data field. And in CAN XL, we have two polynomial. We have in the prephase, a prephase CRC with 13-bit and a cascaded frame CRC with 32-bit. And we can here achieve a real Hamming distance of 6, meaning we can detect any 5 bit failures distributed in the frame. Error signaling is on in classical CAN and CAN FD. However, if we want to use the fast mode as described before, we need to switch this error signaling off, and this is configurable in CAN XL controllers. So also the fast mode switch is not supported in classical CAN and CAN FD. This is why we can't use the PMW coding in these two generations. But in CAN XL, we can configure it and then we can switch it on or off. Bit ratio, I explained already that we have the capability in CAN FD up to 16 times to go faster in the data phase. And in CAN XL, we can go even 40 times faster than in the arbitration phase. In classical CAN, we have just one bit rate and there is no ratio at all. If you look into what you can achieve from the net bit rate, you see here that we have on this graph the net bit rate of up to 40 megabit per second if we're using very long frames with CAN XL, and if we're using shorter, of course, then we can achieve 8 megabit per second with CAN XL. Using 60 megabit per second, we're using just 8 megabit per second, then we are limited to about 7 megabit net bit rate for long frames, and so on. In CAN-FD, you see the blue lines. We are limited up to 4 megabit net bit rate when we're using 8 megabit per second, so to say, the SIC transceiver chips. But where is classical CAN? Oh, you see it here on the bottom, very small. This is classical CAN, just using 1 megabit per second, and the net bit rate is then about 500 kilobit per second, because we have an overhead of about 50%. So the gaining of the net bit rate is quite high, depending on what you like to achieve, and you can select one of the other protocol controller, and then in addition, you can combine this with different transceiver technologies, and so you are very scalable depending on what you like to achieve and what are your requirements. So to summarize this, you see that we have the physical media attachment technologies, CAN high speed with improved symmetry functionality. This will be the future. Then the CAN SIC transceivers and the CAN SIC XL transceiver using the fast mode. In classical CAN, you can have the arbitration bitrate to 1 megabit per second. In SIC, is limited. And then you have also not the capability to use the fast mode for classical CAN, because there is no PMW coding. The same is for CAN-FD. You can't use the fast mode of the CAN SIC XL transceivers with CAN-FD. What you can do when you're using the SIC transceivers, you can go up to 667 kilobit per second, and in the data rate you can go up to 8 megabit depending on your physical layer design. And CAN high speed, you can, if you're just using the normal CAN high speed transceivers with improved symmetry functionality, you can go to 2 or 5 megabit depending on your topology, and the bit rate is going up to 1 megabit in the arbitration phase. The same is for CAN XL. And here you have, in addition, the possibility to use the fast mode transceivers supporting the fast mode, and then you can go 10 plus. How much you can go, this depends highly on your physical layer design. One of the benefits is that if you're using CAN XL, you can, and you're using just the SIC mode, and you enable the error signaling, then you can merge different transceiver technologies into one network. Arbitration bitrate, for example, is 500 kilobit per second. Then you have the FD data phase bitrate to 2 megabit per second, and you have in CAN XL 5 megabit per second or more, or 8 megabit, but there's no mode switch. And then you can still use legacy nodes supporting just the CAN-FD and high-speed transmission, and you can use CAN-FD with SIC transceivers, and you can use the CAN XL transceiver. They can use CAN XL controllers with SIC or with CAN SIC XL transceivers. Anything is compatible. However, I would recommend to use always the highest possible solution, but for those which need to migrate from existing nodes and integrate existing nodes or legacy nodes, then this is an option also for the scalability and how to integrate find a migration path from traditional CAN high-speed transceivers and CAN FD controllers to combine them with CAN XL and CAN XL SIC transceivers. Just to give you an overview on the physical layer specifications from CIA, we have a general recommendation for industrial applications in CIA 102. CIA 103 describes the intrinsical safe CAN device interface specification for those nodes which are used in explosive environments. We have a lot of connector pin assignments described in CIA 106. CIA 110 describes or specifies common mode shocks for CAN networks. And those documents which are given here in italic, they are under development. We're looking for EMC evaluation of CAN SIC transceivers and CAN SIC XL transceivers. This is in progress. We have then also the CIA 601-1 document, which is an implementation guideline for CAN FD physical interfaces. We have a CAN FD node and system design recommendations given in CIA 601-3 in more detail. And we have the cable parameter specification CIA 601-5. And we have CIA 601-4, which specifies the SIC physical medium attachment sublayer, meaning these SIC transceivers, and this has been, of course, already transmitted or submitted to ISO standardization. And we have the CIA 610 series for the data link layer, the conformance test plan, and also the CAN SIC XL transceivers with conformance test, which is under development. There are more CIA specifications. Those in green are related to the physical layer. We have the CAN XL system design guidelines under development. We have the PMW coding implementation guideline in part 2 under development, and they will be released, I hope, in the spring, late in the spring or beginning of summer. The CIA 910 series is very important. There we describe or specify a CAN simulation model for physical layer. And there's also a multi-part document describing the terms and use cases. And then we have the simulation model requirements. And then we have the PMD simulation model requirements for the cables and the connectors and the other things. And we have then also 2 conformance test plans for those requirements. And this is highly sponsored by Volkswagen. And we hope that also this year we will finish these documents. As I said, the ISO standards will be updated, in particular ISO 11898-1. And the new edition to be released this year includes already CIA 610-1, which is the CAN XL specification, and CIA 604-1, which is the CAN FD Lite specification. And this document is recently under development, submitted for balloting. And I expect that the ballot starts in a couple of weeks. ISO 11898-2, this has already been balloted as a draft international standard, was positive balloted, and we, of course, we need to resolve the submitted comments. We received several of them, and some of them are very technical, and we can improve the document. And I hope also this will be released, let's say by end of this year, or when, if we are quite good, then it will be already in fall 2023. Another document which also specifies some physical layer requirements is ISO 15765-5 for diagnostic links to external equipment. And there we have a ballot running up at the beginning of March 2023. And there might be a comment on SIC, CAN SIC support, which is pending because it's not integrated in the document yet, but it could be that this will be a comment, and if OEMs require this, then it will be included in this edition. Also SAE, the Society of Automotive Engineers in the United States, they have a lot of documents related to the physical layer. There are these SAE J2284 series. This describes the requirements for classical CAN interfaces, also the physical layer requirements for the ECUs for 125 kilobit, or 250 kilobit and 500 kilobit, and for CAN FD with the arbitration bitrate of 500 kilobit and 2 megabit, and 500 kilobit and 5 megabit per second. These implementation guidelines and recommendations are mainly related to passenger car ECUs and networks. There's also an SAE J2962-2 document, which specifies the requirement for CAN high-speed transceiver qualification. And we have also in SAE the J939 documents, recommended practices for the physical layer and the design of ECU interfaces and networks. We have different documents there. For classical CAN, we have the -11, -14, and -15, and for CAN FD, -17. And these guidelines and recommendations are intended for heavy-duty commercial vehicles, but also for off-road vehicles. EMC is a big topic in automotive, and there are different regulations by legal entities. For example, the EU Directive 2014/30, or by industry demands on standards, and IEC 62-228-3 specifies test and measurement methods for EMC evaluation of CAN high-speed transceivers under network conditions. This document defines test configurations, test conditions, test signals, failure criteria, test procedures, test setups, and test boards. It covers the emission of radio frequency disturbances, the immunity against those disturbances, and the immunity against impulses, and the immunity against electrostatic discharges. CIA develops also test and measurement methods for EMC evaluation for CAN SIC XL transceivers, and will submit these specifications to IEC for international standardization. But first, we try to specify this within CIA, and then when we are ready and have proven this in test laboratories, then we will submit this for IEC standardization. Just a brief summary and outlook. The CAN arbitration bitrate is scalable from 40 kilobit per second to 1 megabit per second using CAN SIC and CAN SIC XL transceivers. This can be reduced to 500 or 667 kilobit per second. The achievable data phase bitrate depends on the use topology. Have this always in mind, and doesn't say what it doesn't is also always limited by the transceivers. Could be that there are other components which needs to be considered: cables, galvanic isolation, termination resistor, etc. The 3 protocol controller generations can be combined with the CAN transceiver technologies, and CIA develops what's important for the user physical layer design guidelines, including those for long CAN-FD networks and long CAN XL networks. Okay, we are at the end of the presentation from my side. Okay, then I'd like to thank you. And yeah, if there are more questions, you can contact us. So you can consult our website, and we have also some articles about the CAN physical layer in more detail in the next issue of the CAN newsletter in March. You can download the CAN newsletter magazine free of charge. And yeah, when you have questions, you can send them to service where we have the technical inquiries collected, and then you will get an answer. If you want to have more detailed information, you can go to events, and then you see all our education services which are provided. Or you can go to publications if you want to subscribe to the monthly CAN info mail, and this is gives you information on new events, on new specifications and new standards and so on. Or if you don't know to whom you should write, then write just to headquarters and the email will be forwarded to the responsible person. Okay, thank you for listening, and I hope that you have got the information you need. If not, then you can request additional information from CIA or go to another event which we have scheduled. Thank you.